Good morning, everyone. We are going to start today's session, and I'll brief the yesterday's multiple logistic regression, and then we'll go to the breakout room. As that activity couldn't happen yesterday, that's why we are planning for that now. And after you people practice in the breakout room, then we will start with another exercise of understanding what is a confounder, what is a effect modifier, and how to study interaction in case of a linear regression between two variables and more than two variables. So how we did yesterday, coming to summarizing the session, we started with the simple linear regression. We started with correlation. And correlation is basically when you study the relationship between the two variable, the continuous variable. That's the correlation. But correlation only tells you the strength of association and again, whether that association is significant or not. But if you want to know the magnitude of association, that is the beta, then you need to go for regression. Again, regression uses, whenever you go for regression, it's not always a predictive modeling or a model formation. Most of the time you do the regression, as we have seen yesterday in so many articles, that they have just done it, the regression, they have done it to understand the magnitude of association between the dependent and the independent variable. That can be one goal, or another can be like if you are in the clinical scenario and if you wish that everybody else should no, it should come into the policy making, or it should be like used like a evidence-based medicine, then you can go for all those predictive model. Like in COVID, you must have seen a lot of model was developed, and in communicable diseases also we do a lot of modeling. So that can be done. But again, if you are starting in regression, you can start it as an exploratory method. Exploratory, what do I mean by exploratory? Means like just understanding the relationship between the predictor and the dependent variable. And then one step ahead, if you think that, yes, now you are ready to go for a prediction, because for prediction, it's very important that your data, the quality of your data should be very good. Very good means the data collection and the data checking the outlier, interim analysis, all those things are important. So if you are up to that mark, then you can go for prediction also. So in case of this multiple logistic regression, if you see, this was the data set which we were seeing yesterday. So how we start? Let me I will delete this. Select all and then remove. So this way all the analysis will be removed. So if I see the question, we were predicting the length of stay. And if you see the length of stay, in model 1, we have to see the age. Then in model 2, age and preoperative LOS. Okay, this was the simple linear. Let me go to the multiple. Age, gender, preoperative length of stay, complications, complicated diagnosis, and comorbidities. So how we start generally? So how you will, like, you can see these variables, but how you have decided for these variables? If I ask this question, these variables, how you have decided? So basically, if it is a continuous variable like pre-op LOS, or if you are taking age as a continuous variable, so when you do the correlation between these two, and if you see that the strength of association and it is significant, and the significance level which we have set yesterday, that is up till 0.2. And if, like, I think one participant asked regarding whether we can reduce the cutoff, you may reduce the cutoff, but again, that you have to mention like which cutoff you took as a significant variable to be included in your modeling, or to be seen as a exploratory relationship between the predictor variable and the dependent variable. So how you will do? For the continuous variable, you check for the association, that is a correlation. With categorical variable like this, complications or complicated diagnosis or comorbidities, since they are categorical, how you can see whether they are important? So that independent sample t-test in the descriptive, If you perform independent sample t-test and if you see that length of hospital stay, the mean, because length of hospital stay is a continuous variable. So you can check if the levels are 2, then you can do the independent sample t-test. And if the levels are 3, you can go for one-way ANOVA. So if there is a significant mean difference of length of hospital stay in these categorical variable, you may include it in the model. Model means like in the first stage, in the simple linear regression, one by one. So that's the decision making. So one criteria is statistical, the way we have just seen now, either by correlation or by independent sample t-test or one-way ANOVA. If you have seen that there is a strength of association or there is a significant difference in the mean of two group or more than two group, you can include that as a predictor variable. Or as a theoretical framework, if you have reviewed the literature, if you have seen the prior work, and if any variable is affecting or acting as a significant predictor, that you can also take as a predictor. The third could be as a clinical. If you're practicing and as a clinician, you think that yes, that this should be a significant predictor, you can take that also. So the decision of taking a predictor, which, because when you are working on a project, there are many variables, n number of variables. So you cannot perform a linear regression or a modeling with many variables. So how to decide? So that decision we are talking now. So again, to repeat, there can be three decision-making rule. The first is the statistical. That means you perform a descriptive and the inferential statistics. In inferential, you perform the independent sample t-test or ANOVA if it is a categorical. If it is a continuous variable, you can perform correlation and see the strength and significance of the association between the variables. And if it is that is a statistical. The second could be like theoretical framework. That means in the prior literature review, you have acknowledged that yes, these, like in length of hospital stay, there's some prior people, the prior researcher, they have said that yes, the complications or gender or age, that is a significant predictor. You can include that variable also. But again, it is seen that if something is not statistically significant in your data, it is very unlikely that it will come as a significant predictor of your dependent variable. So initially you may include that, but again, you have to see the statistical significance also. And third could be the clinical. So these are the three ways. So let's say I have decided these variables based on the correlation, because in correlation, remember, we have seen yesterday that correlation was there was a significant correlation, 0.14 between the age and LOS, and pre-op and LOS, it was like, I think, 0.314, which was a moderate correlation, and both was significant. So that's why I've included these two variables. The other, length of complications and complicated diagnosis, you can check about the significance level. So how you can check? You can go to this t-test and you can go with this independent sample t-test. I'm not going into the assumptions. I'm just checking now. So this pre-op LOS, you can move here. And then this complications, I can put it here in the grouping variable. I can see the mean difference. You can check for the assumptions also. Let's say I'll check the homogeneity and the QQ plot. And you can, this assumption of homogeneity is met because p-value is more than 0.05. So that's why I will report the student test, not the Welsh. And if you see the normality, so since pre-op LOS, we have seen that it has got only three values, 0, 1, and 2. That's why it is coming like this. And then you can check for the t-test. So t-test, you will see that it is 0.07. So it is borderline significant, you can say. That's why probably you have taken it. And then again, if you see with other grouping variable like comorbid complicated diagnosis. So you can change it and see. So complicated diagnosis, it is not significant. Pre-op. Okay, I'm sorry, this is pre-op LOS. I think I have taken a wrong variable. It should be the LOS. So let me check the first one also, probably because so this was the grouping variable, complications. Again, it is like 0.09. And if you see the homogeneity of variance, it is not met because it is less than 0.01. So I will go for the Welsh T. I won't report the student T. And if you see the difference, so now this is not significant. If you see the length of stay, So ideally, I should not take this variable. But for demonstration, since the researcher has taken these variables, that's why I'm taking it. Again, I can see the other, I can see the complicated diagnosis. Again, the p-value is not significant. Let's say comorbidities. Here the p-value is not significant, so I may see this student t-test. And then you can see this is significant. 0.05 means borderline significant. Borderline significance is here. So I will keep this comorbidities. Similarly, you can check for the other like heart disease or hypertension. Let's say hypertension. So I will take heart disease and I may see its assumption heart disease is not significant. So that's how, if in the you can say this checking of the mean value between these two level, because ultimately regression also gives you, yesterday we were discussing the beta coefficient. What is a beta coefficient? Basically in the regression, if it is a categorical variable, it actually gives you the difference in the mean value between the two. But it is a estimated marginal mean, which I did not discuss yesterday. That means it is a controlled mean. It is not a raw mean. After taking care of all other variable, what is the mean value in the two group? So that's why this way you can check which predictor you should take. Now coming to the regression. So if I go to this linear regression, so how I have done yesterday. So I will take this LOS as a dependent variable and I'll check one by one. So one by one, you can check here regarding the, in the model making. So how I will do, first I'll take, let's say, gender. Gender is a covariate. So I'll put that here as a factor. And then in the model builder, keep on increasing the block. So it is like you can say it is like a forward regression where I'm adding variable one by one, not everything together. So this is block 2. And then in block 2, you may enter the age. Let's say I have entered age. Then if this pre-op LOS was significant, so I'll again, for this, if I want to increase, have this pre-op LOS, I'll again add a new block. And then this pre-op LOS will come here. Complicated diagnosis, if I want to, or complications. So if I want to have complications, I'll again add a new block here. And I'll add this complications in the factors. So this is how, what does it show? It shows the model fit statistics, the R square. So if you see the R square, the model 1 R square is 1%. That means with gender, it is only predicting the 1% change, 1% variance in length of stay is due to the gender. If you see the model 2, the R square is 3%, this thing. If you see the model 3, it is 16%, and model 4, it is 18%. So in model 4, what all, and if you see the change in R square, this tells you the change in R square. Means the change from model 1 to 2, the R square is 2%. Model 2 to 3, the R square is 13%. So second model is a good one because there is an increase in R square. And in the third one, you see only there is a 2%. Third to fourth. So again, the increase is less. Coming to the this coefficient, again, you can check from here. What is the model coefficient? So if I was there in the first model, which was only gender. So if you see the estimate, right now, if I see estimate, from this, before I start with, first we have to check for the assumptions. So don't skip this. How I will check? So you can check this autocorrelation. What is the autocorrelation? Autocorrelation is something like when you measure something and you see that the values if you are measuring something serially, then the values which are closer initially, like I have explained with the help of that skin caliper that you are measuring, and then values, when you enter the data like that, initially all the residuals, it will be correlated. And then when you practice too much towards the end, also it will be correlated. So that is known by the autocorrelation. That should not happen. So for that, we check with the Durbin-Watson statistics. And this Durbin-Watson statistics, that should be, many people say you can take up till 2, up till 2.5. But again, conservative, if you want to be conservative, up till 2 you can take. So there is no autocorrelation in this case. In the collinearity diagnosis, you can check with the all variables, the VIF and the, but for that, it is only giving you the VIF of one factor. So for that, I need to have a fourth model here. So if you put this model 4, it will show you all the VIF. So VIF, what should be the value of VIF? We discussed yesterday, it should be less than 10. So all the VIF are less than 10. So we can take these predictor in our independent as a independent predictor. In the QQ plot, you can check for the QQ plot of all the, you can check for the residual plot, and you can also check for the Cook's distance. Okay, yes. And I think when I'm discussing the Cook's distance, yesterday I think Sri Parna asked regarding the Mahalanobis distance. Yes. So after this, I'll tell you that because we checked yesterday, it was there in the 2.6.26 version. So this is your QQ plot. So QQ plot, it is showing that it is linear, normal in distribution. This is the residual plot. You cannot find any pattern. Again, you cannot find any pattern like fanning and all. So homoscedasticity is there. And again, Cook's distance, if you see the Cook's distance, so the mean Cook's distance is, it's 0. That means it is less than 1. This is the Cook's distance. Maximum it is 0.08. So there is no influential point, because influential point is decided by the Cook's distance, which takes into account of both the high leverage and the outlier. What is the outlier? The value of the dependent variable. If it is too high, that is an outlier. And here the outlier statistics, it is in the form of a residual statistics. And what is a high leverage? High leverage means the predictor variable, if any predictor variable is very high, and because of that, it is showing, it is dragging the regression line from the best fit, then it is the high leverage. And in Cook's distance, it combines both. That's why we take the Cook's distance. So in that Mahalanobis distance, probably I'm not pronouncing it right. So that is the high leverage point, because high leverage, that is again a objective measure. That distance is an objective measure to measure the high leverage point. But again, Cook's distance is better because it takes both the high leverage and the outlier. So that is there. And the model fit, you can come to this, then you can see this, like intercept and male, female. How will you interpret? 0.35 means there is a 0.35 difference of length of stay between male and female. If it is 0.01, then how will you interpret that? If the age is increased by 1 year, the length of stay increases by 0.01. Similarly, what is 0.74? 0.74 means if you increase the pre-op, length of stay is more, then again, the length of stay is more. And these complications, yesterday we have seen that it is showing the opposite. If it is more complicated, then the length of stay was less. So that is how, again, in the table, you can click on the standardized and unstandardized residual. If you see the model coefficient is, this is the confidence interval of this estimate. So this is the lower and upper confidence interval, and standardized estimate is like, you can compare these beta. So if you see, if I click on the standardized estimate, it divides the standard error. This divides by the standard error of the residual is known as the standardized estimate. So this is a standardized estimate, this column, this one. And if you see, now you can compare here, like which one is the better predictor in terms of beta. So now if you see, this is the complication has got the highest value, 0.47. So this is how we interpret it. I'm not telling you the estimated marginal mean now. And you can, when you will come from the breakout room, then I'll explain the other concepts. And in the save, you can click on this. You can see the predicted residuals and Cook's distance. And in the data, 3 variables will appear. So these are, I think many variable has so many residuals. So actually I saved it. That's why so many residuals have appeared. So this is how you can check for residual was like difference between predicted and actual. That was the residual, which we have done yesterday. So I think we will go to the breakout room now and we'll practice up till this point and then Dr. Farzana has asked one question. In many article, people are reporting multiple models together. What should be the ideal way to report? Only good one or more than one? So you can, it is up to you actually. Generally, you will see that people report, you can do it in the write-up that you tried these, and many times you will see in the footnote they write that in model 1 was with these variables, but finally they propose one model. So it depends on the number of pages, word count, number of tables. It is up to you. No way. If you wish to show all the model, you can show. If you wish to do that, the earlier model, how you have reached finally to this final model, you can give that. You can also give a supplementary because they ask for supplementary material also. So you can write all those model detail in a supplementary sheet and give in the main manuscript as a final one. Okay. And then Dr. Sunil has written, Dr. Manju is asking, what about the sample size? So sample size is again for the regression. Means like model number of variables. That you want to ask the sample size for? Can you show the chart? Okay. So generally it depends on the number of predictor variable. So in you see in case of a linear regression, how do we calculate the sample size? I think in case of logistic, that is okay. But in case of linear regression, a number of predictor variable, I think you have to take the effect size. So effect size in this case is the beta. So the beta, then which beta to take? So from the prior, you can say research, you can take the appropriate beta. Appropriate beta means because with the lowest beta, it will give you the highest sample size. So the lowest beta, the variables with the lowest beta, you can calculate the sample size for that, and that will be applicable for all. So you can calculate the sample size using effect size. That is there in the this thing, G power. So in that you can calculate using effect size, because in the statulator and everything, it is not possible to calculate the sample size for linear regression. But again, it depends on your objective. If your primary objective is to predict or give a prediction model, then you can take beta as a effect size. Beta means that coefficient, not the standardized one, but the raw coefficient. Am I making myself clear, Dr. Manju? Okay, in the G power, you can calculate it. But again, I said that in statulator, you don't have the option of doing the calculation using effect size. Effect size calculation is there in the G power. So you can use G power for calculating the sample size for linear regression. There you will see the option of effect size. From there, you can select beta, enter the beta, again give all those inputs like alpha and beta error, and it will give you the sample size depending on the number of predictors also. Okay. So now, so how was your experience? Any other questions before we move further?
Yes, ma'am. Just in our breakout room, there are a couple of questions.
Yeah.
The one question was like, we have we are getting the understanding about the interpretation of the categorical variable. Still, there are some confusion how to interpret if the
Like,
complex.
Like, can you, like, I am showing the table and you can tell where is the where is the problem?
Like complication, yes and no, and the beta value is minus 0.77. So how exactly we should interpret it?
So the interpretation will be in the people who are having complications,
Okay.
since it is minus sign, that means the dependent variable will be less. That means the length of stay will be zero point 0.7 days. And you have to, of course, calculate because length of stay here we have measured in days. So zero point 0.7 means you will convert it into hours. So 0.7 days less in people who are having complications.
Okay. That's
Actually, it's only the difference. Remember, see, just now we discussed the mean change, a mean difference in the independent sample t-test. Can you recall? In descriptive also, in inferential statistics, we have learned that independent sample t-test tells you the mean difference between the two group. This beta also gives you the mean difference only, this beta.
okay, ma'am.
But again, it is adjusted one. That means there it was a raw one, means only one variable. Here it gives you the complications, keeping like other variable constant. That means it has taken into account of the other variable. That's why there is an importance of linear regression. Because here it is isolated the effect of complications. It is not getting affected by any other variable. So if you keep other variable like pre-op days, age and male constant, gender, then only complications, like person who is having complications will have a zero point 0.7 days less stay, a length of stay, like post-operatively. That's
Okay.
the interpretation.
Okay. Okay, ma'am. And second question is like when we are adding the model block. So
Yes.
there are two options. What I recalling from yesterday's session, like block 1, block 2, and block 3. In
Mhm.
block 1, 2, 3, and we are adding the independent variable one by one.
Mhm.
And the second option was like that what that I am not recalling and not getting the understanding. In under block 1 also we are adding independent variable. So
No,
what the difference?
okay. So what you can do, like here you are making so many models, like
Okay.
one by one. But if you don't want to go like that, this is known as the forward way of doing the linear regression. Means you are entering variable one by one. But let's say you don't want to enter the variable. I will again, I'll delete all these analysis. So I'll go to all and then I'll remove. Again, I'll go to the regression. I'll open this linear regression and I'll move. So now I'm not going blockwise. What I did, I know beforehand that these are the variables which I have to take in my model. So I will take this LOS. See, there are many ways like backward, forward, enter. So in SPSS, you will find there are a lot of ways. In GEMOV, you can do like forward like this, adding one by one, or enter method means all together. That means LOS, I'll move here. The age as a covariate, pre-op LOS as a covariate, gender here as a factor, complications here as a factor. Let's say I'm only taking these four variables. So it will give you overall, it will not give, if you see here, it doesn't give you all the model. It will not give you the change in R square also. It will only give you like total of 18%. The variance means the variation in the variance in the length of stay. You can predict 18% variation there using all these four variable, which is the age, pre-op, LOS, gender, and complications. And then this is the interpretation, like this is the beta. The value will be same like model 4 because that was the final, but there you can compare. And if you wish, like I think you were asking like whether you should give like all the details of all models, or you can go only like enter everything together and then see. In that case, you cannot see the effect of like what was the change in R square with each model. So that shows like you have worked up till this extent and maybe you are adopting a final model, and you have said that, and we have also seen that many people do it like that, may make multiple model, but that hierarchical and enter those forward selection. We only enter all these variables and they report this table. So you can use that also.
Okay, ma'am. And the
That's why we say control. And we will have a session. This is known as confounding. So, like complications, you can have the age can be a confounder here, because you see that complications are more in people who are having like older age. So that can act as a confounder. But if you have entered it as a co-variate and factor, then it controls for that confounder. So that's why you will see that in epidemiology, many people and our guide used to ask, like, how do you control for confounder? So that classically, that time we used to say you can control it when you are doing the sampling, when you are selecting the individual, you can remove biases, and then you can control it statistically also. And regression was one of the method of controlling the confounder statistically. So here, if you enter it as a covariate, even if it is a confounder, it will control for it, and you will have a isolated effect of these complications over the length of stay. It will not be affected by any other factor, let's say age or any other gender.
Thank you so much, ma'am. Now I got the clarity.
Okay, you are most welcome. Any other question?
Ma'am, I wanted to ask that what is the importance of knowing the difference in R square? Like when we put all the independent variable in a hierarchical model, like in blocks. तो
Mhm.
मतलब by knowing the difference in R square, can we remove having the difference R square,
Improved the model variance by 13%. So it was the most important factor, predictor, you can say. Because when you have included that factor, your overall model accuracy rather, or the variance prediction improved to 13%. So that change R square shows a very important predictor.
so we have to mention this in our result. मतलब we should show it in our result.
I said, see, you are at what level, it depends. Like, again, I said, like, if you're a postgraduate student doing a PhD thesis where a lot of other things are also there, then probably you can only comment like this. But maybe if your primary objective is a prediction, are you getting my point? It
Yes,
depends
ma'am.
what is my primary objective. So linear regression, there are two purposes of linear regression. First is to know the amount of magnitude of relationship between the predictor variable and the independent variable. So if your aim is only to know the amount or magnitude of relationship between the predictor variable and your dependent variable, then you can use this method, and there's no need to show like all these model 1, 2, 3, 4. Okay, but
Yes,
when
ma'am.
your primary objective is prediction, because in clinical setup we also we receive a lot of proposal where their main aim was like a prediction, like predicting COVID death, predicting ICU admission, or probably here also in this thing, length of stay or discharge, early discharge. Because if like in the emergency, if you need the ventilator, so what are the factors which will help the early bed emptying, or the bed occupancy, and all those things, where your main aim, because in this case the article which we have shared, their main aim, because that was in a decision maker, this thing. So if your main aim or objective of your research work is prediction, then you need to show these changes in the model, because then the reader will come to know, like, you have tried with all. Because if you give a final one, then the reader will not come to, or even the decision maker, because the decision maker, if it has come to as a policy change or evidence based medicine, then you have given everything, all the predictor. That might come to somebody else's mind, that, oh, you have not taken that, oh, that should have taken. So all those speculations you are like taking care of. That's why you are showing like this model one, all these, and that's why you mention each and everything. There you have to show, like in all inferential statistics regarding the correlation, regarding independent sample t-test, why you took those predictor in your final model, and final model, whatever you are proposing, that is after comparing 3-4 models. So you have exhausted all the options, and that's why you are proposing this. In that case, it is imperative, it is essential that you show all possible model and show the change in R square.
Okay, ma'am. Thank you so much, ma'am.
Did you get it? So is it clear to everyone? See, it depends on the purpose of your research. Linear regression serves both the purpose. But many times you will see that we are not into this prediction. We are only just, we want to know the control the confounder. We want to understand the relationship as an exploratory. In that case, you don't need to show these 1, 2, 3, 4 model. You can only go with the final one, or you can only show this like this, the way I have just shown. But we have told you both. So depending on your objective, you can adopt a particular way of doing it. And this is only in Jamovi. In SPSS, there are many more, which we are not covering. But in Jamovi, you can do like with the forward selection, going like one variable at a time, or you can enter all together as an enter method and give a final model. Am I making myself clear to all of you?
Ma'am, yes, ma'am, and one question, ma'am.
Yeah.
Ma'am, I'm going to propose the topic, ma'am, development and validation of a prediction tool, for vasovagal reaction, blood donations, ma'am.
Okay. So your main aim is prediction then?
Yes, ma'am. Prediction tool for vasovagal reactions among the blood donors, ma'am. So I'm going to develop and validate the tool, ma'am.
Okay.
So the first portion is I plan for the FGD. FGD among the transfusion experts and some phlebotomist. So and then I'm going to develop a tool with the help of the expert opinion. So after the tool will be developed, then the tool will be go for pre-test, pilot test, and the other things, ma'am. So after that, I'm doing the linear regression. I'll go for a linear regression. Is it correct, ma'am?
Yes, you can do the linear regression. Again, you can do, there is something known as a structural equation modeling. That is also like after that confirmatory, I think you have attended the EFA, CFA, the scale validation workshop. If I
yes,
recall.
ma'am. Yes, ma'am.
Yeah. So after you have developed the CFA and you have proposed the structure, then there are two ways. Either you can go for structural equation modeling or you can go for linear regression.
Okay, ma'am. Okay.
Both are like, because there you will be telling about all these confounder, that is, we call it as a DAG, means directed acyclic graph, where you propose that there is a mediator. This is the causal pathway, how that vasovagal or whatever your aim is. So you can go both ways. You can go with linear regression also. It is okay, because there you can take dependent variable as your score, whatever vasovagal, and then you can take the other variable which you have finalized the structure in your confirmatory factor analysis.
Okay. Ma'am, and one more question, ma'am. If it is I'm moving for validation, means all the blood donations will happen. Most of the blood donations happen on the outdoor units, ma'am. So if it is developing from one settings and validation from one setting, some statistician told me. So the camps, ma'am, most of the camps in outdoor units only, ma'am. So why I'm going for other settings?
Generally, he said that data from where you are collected, it will be applicable to that setting only. Because the people, that's what your question is, if I got you right.
Yes, ma'am. That's the question.
So generally sampling. So there's a role of sampling from wherever you are collecting your samples. So, your result will be applicable. That is the external generalizability. So external generalizability of your result will be applicable to those population only. You cannot apply it to everyone. If you want to apply it to everyone, then you should have a representative sample from all the sectors.
Okay.
Okay.
Okay. Thank you, ma'am.
You are most welcome. Any other question in linear regression up till this point, whatever we have covered, any doubts in any breakout room or any individual person? Otherwise, we'll go to the next part, that is the interactions, confounder, and estimated marginal mean. These three topics are left, which we want to cover. Let me see the chat. I think no questions, so I'll go ahead. Now, coming to another concept, if you see here there is an option of estimated marginal mean. And we are going to see what is this estimated marginal mean, this one. So I have not explained up till this time what is this estimated marginal mean. If you click this, you can see here that it again asks for like which marginal means you want. And then there are a few other options like equal cell weights and marginal mean plot and marginal mean tables, etc. So we will explain you now how this marginal mean is different from the traditional mean, which we know, and what is the importance of this marginal mean in case of ANOVA or regression. So coming to that, generally, in case of like controlling, okay, I think before that, I think I should tell you the concept of confounder and interaction. Okay, so before that, let me take the session on this confounder. Then I'll tell you that. So there are two phenomena, basically in epidemiology or whenever we are trying to see the relationship between a predictor and a dependent variable. One is there are many, but we are dealing with two types. That is one is a confounder and the other is an effect modifier. Statistically, this effect modification, we call it as an interaction between these two variables. I think many of you must have heard these two terms. Confounder is a very common term. We used to ask from our UGs also in Viva, and everywhere it's a very common thing to ask. Interactions, many times we ask from PGs and like effect modifier. So now we'll see briefly, because it's a huge topic again, but just for the purpose of linear regression, we have tried to like minimize the concept so that you can understand it. So now in regression, because in regression you see that there are many variables, many predictive. Generally, we don't go for regression with only simple linear. We take many independent variable or the predictive variable to see the relationship between the dependent and the independent variable. So when we use regression, can we assume that all variables act independently? Like if age is there, gender is there, length of stay, pre-op length of stay is there, comorbidity is there. Is each variable is acting independently or in combination with the other variable? Naturally, what can you assume? Yes, please answer in the chat box. So answer will be yes or no. So there is a mix of answer between yes and no. So variables never act independently actually. It will always, because it is from one person only, na? See, if you are taking gender, it will be of one person. If you are taking age, it will be my age, or maybe if I am the person. If you are taking complications, it will be from the person. So all the variables are from the same person. So it cannot act independently. You know that there are females are predisposed to some other, like there is a mix of, a person has got multiple variable. All the variables which you are seeing here, like length of stay, gender, age, complications, hypertension, diabetes, that is from a single person. I mean, all the yes and no is from a single person. So any variable cannot act independently because it is from the same person. So a person has got multiple variable. So if you wish to like isolate my gender effect from my health or my age, if I'm aging, definitely I'll be having more complications. And if like as a female, maybe if someone is postmenopausal or premenopausal or during menarche, if I'm a woman, then I may have some health problem because of that also. So any variable never acts independently. It is always in, we talk about it, but it is always in in relation to each other. So answer will be no. No variable act independently. We talk about it, but biologically, whenever in the real world, there's a mix. Everything is getting interacted with them. We cannot study so many interactions because then it will be very complex statistical part. So that's why you see that we study up till like two-way interactions, three-way interactions, many people. But again, those four-way and you will not see very commonly. So that's why generally the variable, they never act independently. They act in combination of the other variables. So sometimes they interact with each other, sometimes they distort the relationship, sometimes they mask the relationship, sometimes they increase the effect, and sometimes they reduce also. So that's why the concept of confounding and interactions come in. So now what is confounder and what is an interaction? So coming on the first concept, that is a confounder. So what is a confounder? So basically, whenever you are seeing the effect of one predictor over the other, and if the third variable is distorting the true relationship, it is known as the confounder. That means it is something external. Actually, that relationship is not there, that magnitude is not there, but because of a third variable, you cannot uncover the true relationship. That is the confounder. What is a interaction or effect modification? Effect modification is the is inherent nature, some biological this thing. When a third variable, it changes the effect of another. That means actually that relationship is there and you are uncovering it. So effect modification is its effect, or effect modification is like understanding the true nature. Whereas confounder is like you are removing the dirt. Dirt means if you have to see something very clearly, and if you remove the dirt and then see it, that is, dirt is like a confounder. But the interaction is like something is there hidden inside. And if you are increasing the power of your lens, zooming in or zooming out, that is like an interaction. So have you understood basically what is the difference? So let's see if it is a camera. Let's say if it is a mobile camera. So if you are just cleaning the lens of your mobile camera to see something clearly, it is like a confounder. If you are like zooming out something just to have a clear picture, it is an interaction or effect modification. So this confounder, it adjusts the magnitude of effect, and it basically alters the direction or strength of effect. It may alter the direction or strength of effect also. So confounder, we always control for it. So we enter it as a covariate in the model. But interaction or effect modification, there is a separate way of studying that. You enter those two variable as an interaction, and if the p-value, or if it is a statistically significant interaction, if it is appearing in your model term, then you say that these two variables are interacting with each other. So basically we explore it and we report it. Now coming to the same example of the data set and the article which we have shared. Suppose we are studying the length of stay after surgery, and we want to see that whether gender affects the length of stay after surgery or not. That means whether female are staying more or males are staying more. But someone might ask, like, what about age? Would that be confounder? So, but can age be associated with gender? Yes. Can age be associated with gender? Suppose you have selected the individual where your population was from 18 to 60. Okay. So in female, probably you have selected the female mostly which are more than 40. And in males, you have selected males which are like less than 40. So can you say that age is associated with gender here? Yes, please answer yes and no.
Yes, ma'am.
Yes, because when you are not careful regarding the selection, it may, because if your selection criteria of age is so large, like 18 to 60, then definitely that will be there. But how can you test that in the inferential statistics? Can you test that in the inferential statistics? So you can see the mean age. That's why I said before regression, you should do a basic of all that inferential statistics. If you see the mean age, between male and female. And if you find a significant difference, then definitely age can be a confounder. And then if you conclude that yes, females are staying more, length of stay is more, but it is not because of gender, because females uh, whom you recruited, mostly they are above 40 or above 50. So mean age was more. That's why probably because of age, they are staying more. Okay. Are you getting the point? Like, am I making myself clear to all of you? Okay. So that's how here it is not a causal this thing. So you cannot say that what is causal. So I said that causal means like X is causing Y. So here you cannot say that age is causing gender. So how do we define confounder? It is a classical definition that should be associated with both the predictor and the outcome variable, and that might independently cause the outcome, but that doesn't cause the predictor. Means the age here will not cause gender. Okay. So that but it can be associated with gender. So that's what we have written here. Like maybe males, they have an average age of 22, and females, they have an average age of 31. But again, age is related to LOS. Yes, because the patient who are older, their chances of staying for more in the hospital will be more, because with age is again a predictor. Age can be increase the length of stay. So in this case, age is a confounder. Why? Because age independently can increase the length of stay, and age is associated with gender, but age is not in the causal pathway, because age does not cause the gender. Only because of the sample, this thing, you have not adopted a correct sampling strategy. So that's why you are seeing that mean age was different. So that's why I said that in prediction, all these things are very important. Sampling has got a very huge role in case of a prediction model. If the sampling method was not accurate, if you go just by convenient sample or purposive sample, or you select whomsoever is coming to you, then there will be wide variation. Variance will be so huge that whatever you will predict, there will be a lot of confounder and the interactions in your data set. So yes, this age is also related to length of stay. So you can conclude that yes, age is a confounder because it is associated with gender and it is influencing the length of stay. So it can be a potential confounder if I want to see the relationship between the gender and LOS. So gender is my main variable. That means main predictor variable, and age is acting as a confounder. So a confounder does not have to cause the predictor variable. Means the predictor age does not cause the gender. That you have to remember as a definition of confounder. So what questions will I ask to judge whether something is a confounder or not? So I will ask this question: is age associated with gender in our data? So yes, it is associated in our data set. If you see the average age of male, this age in males, it is 22, and female, it is 31. So it is not evenly distributed in both male and female. That we will see. And now again, if I ask like, is age associated with length of stay? So yes, because older patients. So I think let's see this before I go further. So how will you check that? You have to go to the data and open this analysis, go to t-test, independent sample t-test. So I will put this gender as a grouping variable, and I'll put this age as a dependent variable. And then let's see the homogeneity and normality assumptions. Sorry, QQ plot, because sample size is more, that's why I will not go for Shapiro-Wilk. So homogeneity of variance assumption is met because p-value is more than 0.05, and this is somewhat linear, means the QQ plot shows that it is normal distribution. So I can go with the independent sample t-test, and I can see the mean, this thing. So if you see the mean difference in age, so mean difference is in male and female, it is 0.276. And which is not significant. So in our case, probably it is not significant, but it may be significant, mean age. Now seeing the another variable, what was the another variable? Length of stay. So instead of age, if I take length of stay, so this was the length of stay. And I may see, so length of stay, again, the difference was significant. If I see this, there was a significant difference. P is significant. And if you see the length of stay, it takes like 0.39 less. For that, you need to see the descriptive. So if I click on descriptive, you see like in female, it is 4.13. In female, it is 4.13. In male, it is 4.52. So which has got a larger stay? Female has got a less stay. Okay, so if I see that age, whether age is a confounder or not, so for that, I need to see whether it is affecting the relationship or it is modifying the relationship or not. Is it only due to this, or age is also like playing its role? So that's how you can decide whether by doing this inferential statistics, you can see whether age is associated with gender or not. And then again, you again need to ask this question, like, does age lie on the causal pathway between gender and length of stay? So no, it does not lie on the causal pathway because gender does not cause age. So that's why age is not an outcome of gender. Then again, can the age be a confounder? So yes, age can be a confounder because it distorts the relationship between gender and LOS. So what should we do if the age is a confounder? So basically, we will include age in the regression model as a covariate, and that will adjust, like what Farzana was asking regarding the complications, plus and minus. So when you enter the gender, age, everything as a covariate, then it adjusts for that, even if it is a confounder. So how will you label that if something is a confounder or not? Because you have entered it. But if it changes the beta coefficient by more than 10%, then it acts as a confounder. Otherwise, it doesn't act as a confounder. So to first, you are taking this in the inferential statistics, taking help of the independent sample t-test. But in linear regression, when you are performing linear regression, how do you decide? So you decide on the basis of change in beta coefficient. If by adding the variable, the another variable or covariate, if your existing beta coefficient changes by more than 10%, then you say that it is a confounder. Now, what is the effect modifier? Okay, so now let's say if we are studying that does age influence the length of stay? So we found out that in patients without complications, age has got little effect on length of stay. But in patients with complications, older patients tend to stay much longer. That means you can say that the effect of age depends on the complication state. It means the effect of age is different in the complications and without complications. That means you can see that it is a statistical interaction. Again, you can again check for it whether something is a interaction, because these are not very simple things. So you need to check it. You should have some theoretical background also, and you should check it while you are performing statistical. A same variable can be a confounder and can be an effect modifier also. So we'll see that. So in the real world, effect of one variable on the outcome, it is not often same for everyone. So that's why all that characteristics may modify how strongly that effect of predictor variable on the dependent variable is. And this is known as the interaction or the effect modification. Now for effect modification, what question should we ask? So again, in this case also, here, if I ask that, like, does age affect length of stay? And if the answer is yes, because the older patients tend to stay longer in the hospital. If I ask, like, does complications affect length of stay? I can say yes, because patients with complications here, they have got a shorter stay depending on the management. And then again, I may ask, like, effect of age on length of stay. Is it different based on complication status or not? So yes, because age increases the length of stay only if there is a complication. So that means there is an interaction between the age and complications. So that suggests that there is an interaction, because the effect of one variable depends on the level of another variable. And this is the interaction. So in interaction, you have to enter the term as an interaction. and then you have to report it. So how do we do that? So if I'm just seeing, because in length of stay also you people were asking why that length of stay was less in complications. So now we can see, we can enter that as a age, so how to do that? If I want to enter it as an interaction, so in the same block, this arrow, this one is for the interaction. So how you will do that? Click age and press shift and complications. So just a sec. Not shift, but rather control. If I want to uncheck that, age and press control and press complications, and then enter it here. So if you enter it as an interaction, you will see like this term, it will appear like this: age, there's a star, and there's a complications. So this term will appear in your model. And here you can see. But again, you can see here that it is not significant. It is 0.665. So if this term is not significant, this one, then your interaction is not significant. Then you can say that, yes, there was no interaction between the age and complications. And again, you can see this is the estimate. So if it is not significant, then there's no need. Again, if I wish to have some other this thing, let's see. If I gender and complications, I'm just doing random now. So I'm going random and complications. If I enter that as an interaction, again, it is not significant. So now how to decide what variable you should enter? So that again depends on your theoretical background, your previous prior literature work. And here also you can do that. If you wish to do that, you can at least two variable you can enter it as a, if you are finding something unusual, you can enter it. Let's say if I enter this pre-op LOS and complications, and let me move this first back. Again, this is not significant. So none of the interaction, because I was trying to find out why in complications length of stay is less. That may be because of a not a true this thing, means something hidden is there inside. If I enter this age and complications, again, this is also not significant. So this I have tried to have means I have tried to study the interaction of complications with all these three, but none of the interaction was significant. So I can say yes, definitely. Then I don't have any other reason by mistake that complication is also. So I cannot say that why this 0.77, since it is a data which is not the actual data. But again, in the actual article, if you see, there also they have shown that it is in the complications it was less. But so this is how you study the this thing, interaction. And for the confounder, again, confounder, so if you move those variable here, then you are controlling for it. So if you have moved gender here, age, so all, if I'm seeing the effect of age only, then it takes care of all the three other variable. So in the confounder, then you need to, if you wish to mention on the confounder specifically, then again you need to enter it one by one, seeing the effect on beta, because here you cannot see the individual effect on beta. Everything will come together. So that 10% change which I was saying, that you can only do if you enter it one by one, like the model which we have shown you. Like if I want to see whether gender is this thing or not, so what I'll do, I'll select all, I'll remove this. So again, I'll go to this regression, linear regression, and I'm moving this LOS here. Let's say I just want to see the effect of gender. So I'll put gender as a factor. And if I want to see whether age is a confounder or not. So the effect of beta is 0.39. Now, if I need to see the change in beta, so I'll add a new block. And again, I'll move this age here as a covariate. So if I enter age as a covariate, then it is 0.36. And in model 1, it was 0.39. So there was a change in 0.03. So 0.03 is what percentage of 39? If I calculate, 0.03 means 3. So 3 divided by 39. So it is 7%. So that means it is not a confounder. It should be more than 10%. The change in beta should be more than 10% to say that it is a confounder. Are you people getting what I'm telling? I don't know. Can someone say yes or no?
Ma'am, could you please repeat this part, ma'am? I couldn't get it properly.
Okay. I was saying, like, while I was explaining the theoretical part, how you can say that a particular variable is a confounder. So traditionally, that, like, see, the example which I gave here, I will only tell you with the example. Why? Because then you can apply the same example in your setting. Yes. So remember, I was telling this, like we were discussing like age and gender and length of stay. So my main predictor variable was, if my question is, I am studying whether gender affects the length of stay or not. Okay. So I have this predictor variable gender and my dependent variable is the length of stay. Now I just wish to see whether age is a confounder or not. Means maybe if I'm seeing that mean age in my male and female, it's different. Like if the male average age is lesser and female average age is more. The example which I was giving. If something of this I have experienced in my data, then I may go for see whether it is a confounder or not. So how will I see whether it is a confounder? So if addition of a third variable changes the initial beta by 10%, more than 10%, then, I mean, that increase is more than 10%, then you say that it is a confounder. Okay. So for here, so the same thing I applied here in the gem movie. But for that, I said that if you go by enter method, when you enter all variable together, then you will not be able to appreciate the change in the beta. Change in beta, I'm calling this change in beta, that means this change in the estimate. This one. Change in, not for the constant, but for this. This one. So what I am saying that if by the inclusion of a third variable, if my beta changes by more than 10%, then that variable is a confounder. Did you get it up till this point? Then I'll move ahead.
Yes, ma'am. Yes, ma'am.
I have one doubt.
Okay. So should I first let me complete the other two people doubt, then I'll come to you, Priyanka. Or is it, if it is related to this process, then you can tell it now.
Ma'am, it is related to this one only.
Okay.
Suppose we will take gender as a confounder. We want to check. Then shall we put gender under covariate?
No, we are not taking gender as a confounder. We are taking
Suppose, ma'am,
age.
suppose. Suppose we want to take gender as
No. Then in that case, which is your predictor variable? Age?
Maybe age.
So that window will be same. Covariate means don't go by this name. Both here as a covariate only.
Okay.
Means there is a separate boxes for categorical variable and continuous variable.
So, okay, ma'am. That is what I was asking.
I think you got confused that we have to enter here only because I was.
Here only. That's
I'm
what
sorry.
I was saying.
I'm sorry. Rather, you can, depending on whether it is categorical or excuse me, continuous. You can enter it anywhere.
Okay.
If you have understood up till this point, then what I was saying, I will move. I am taking age here as a confounder. So now, if I have moved that back, now see, this is my model 1. So what is the value of beta coefficient here? Yes, all of you please write. What is the value of beta coefficient when I have only one predictor variable? 0.39. Now I have taken age also. So I will move this age here as a covariate. Okay. Means as a another factor. And then you see. So now my beta coefficient from 3.9, it has come to 0.36. It has gone down. Okay. Now I have to see this change. So what is the change? What is the value of change? Please write it in the chat box. 0.39 and 0.36. How much is the magnitude? 0.03. So that's what I did. I have calculated 0.03 in the calculator that it is of what percentage of the initial value. So I calculated, like, you can remove decimal 3 divided by 39 because 39 was the initial one and this is 7%. So the change in the reduction in the beta coefficient is less than 10%. That's why it is not a confounder. Have you understood, all of you?
Yes, ma'am. Yes, ma'am.
Okay. Now, if you have understood up till this point, then I'll go to the another part which I have not covered till now. That is the estimated marginal mean. So once you have done up till this point, now you may report the estimated marginal mean. So now what is this estimated marginal mean and how this is different from the traditional mean that we are going to see now. So estimated marginal mean, you can call it as an adjusted mean because till now you have seen the adjusted coefficient. But what is the estimated marginal means, that how do you report it and when you report it? So suppose this is one example. This is a data set of like 10 people, 10 male and 10 female. So in the first column, there are 5 males and 5 females. In the second one, they have undergone two interventions, diet and exercise. And this is the outcome variable, which is the weight loss. Okay. So the researcher planned to compare the effect of weight reduction in two interventions, diet and exercise. And we want to adjust the effect of gender. So this is the data. Now, if I have to, then see, the software gives you the value of estimated marginal mean, but you have to give the command. So to make you understand how this estimated marginal mean is different from the traditional mean, the software arranges the data like that. So what it has done, so all the male, if you see this, 3, 3, 3, these are the value in the diet, and in female it is 7, 8. If you see the previous one, so it is male. So male, you will see that in the diet group, there are 3 males all having the weight loss of 3 and 3 and 3. That's what it is written here. In the female group, in the diet one, there is a weight loss of 7 and 8. So this is the diet and the weight loss is 7. And this is the diet group and the weight loss is 8. So I have arranged the data like this. In the female, it is 7, 8. And then in exercise, there were 2 males. So 5 and 6 is the value of exercise, the weight reduction. And in female, this 3, 5, and 7 is the value of weight reduction. So if I have to calculate mean weight loss with dietary intervention, how will I do that? So I will add all 3, like 3 plus 3 plus 3 and 7 and 8. So that is our mean. And if I have to calculate the mean weight loss in exercise group, how I will do? So I will like take a mean 5 plus 6, 3 and 5 and 7. So this is mean. But we are not, right now, we are not considering the gender effect. We are only seeing the mean weight loss in the dietary intervention and mean weight loss with the exercise intervention. And if you see, then you can comment, yes, the mean weight loss in diet is less and the mean weight loss in exercise is more. Can you comment like that? Seeing this, yes, please answer yes or no.
Yes, ma'am.
Okay. Now, if the researcher wants to see the effect of gender, then how that mean will be calculated? So in each cell, it will have a mean. So in the first cell, what will be the mean in the diet? It will be 3. Do you agree? Mean of this 3, 3 will be 3. Yes or no?
Yes, ma'am.
And mean of this 7 and 8, mean weight loss only in female. What will be the mean weight loss in the diet group? 7.5. Similarly, what will be the mean weight loss in exercise group in male? 5.5. Do you agree? And mean weight loss in female in exercise group, it will be 5. If you like add it, 7 plus 5 plus 3, it will be 15 divided by 3. Now, so if I ask like what is the mean weight loss in with dietary intervention adjusted for gender? So this I have adjusted for gender. Then you can take the mean weight loss in diet. So 3 plus 7.5 by 2. Mean weight loss will be 5.25. Similarly, the mean weight loss in exercise group will be 5.5 plus 5, which is again 5.25. So if I have adjusted for gender, now can you see that the weight loss is same in both the group? Can you appreciate this? Okay, so if it is same, then you can, this is the marginal mean. Okay, so this, when I was taking this mean, this is the traditional mean. And when I took it like this is the estimated marginal mean. So if you have understood up till, you don't have to do this again. This is just to make you understand. Like you have to report the adjusted means also. So estimated marginal means are the group means after having control for a covariate. And this in statistical model, whether you are doing ANOVA or you are predicting something and you have to do this as a give the value of estimated marginal mean, then you may report it. And that option is there in the movie. So now we'll see. In this column of estimated marginal mean, let me enter the other variables also. Let's do it only with age and gender. So you can come here. Now you have to enter if you want this estimated marginal mean for gender and age, both on the same graph. Then you can like enter these two variables here. And then here you will see that it asks for equal cell weight. So equal cell weight, by default, it is clicked. That means it is considering that cell which you have just seen in that PowerPoint. We made that 4 2x2 cell. So there, the number of male and female is equal. They are equal. So it assumes that. So we generally leave it like that only, equal cell weight. And then this is the marginal mean plot. If you wish, this is the marginal mean table. So this shows. Now, if you see, it gives you the marginal mean of in the here. What you can do, it gives you the what is what is the interpretation of 3.93. So 3.93 is the marginal mean of length of stay in female, and age it takes like 1 standard deviation less. So this 3.87 is the mean age. This is mean minus 1 standard deviation, and this is mean plus 1 standard deviation. So for continuous variable, what it does, it categorizes it into 3 parts: mean minus 1 standard deviation, mean plus 1 standard deviation, and mean. So this is the estimated marginal mean of length of stay. And it gives you a plot also. So if you see this is the plot. So this is the length of stay, and in the female and male, so you can see with increasing with plus 1 SD, the length of stay is more. So by this graph, you can see that. And this is the meaning of estimated marginal mean. So if you wish, you can also show this in the graph. But again, if you wish, like you want a separate for age, then what you can do, I will move this first. I have to enter the age. So if you enter age first and gender later, then the look of graph will change. So this you can see. So here you can see that there's no interaction. This is these are the two graphs. This is for the female, the lighter blue, and the darker blue is for the male. And it is showing that as age is increasing, the length of stay is also increasing. And this is the estimated marginal mean for the same. So this is how you interpret the estimated marginal mean. Now, in this case, you don't get the effect size. So if you like, there's another option through which you can perform this linear regression, and that is the generalized linear model. I think for that you need to install this linear model. Can you see this option? Can you see this option of linear model? Thank you. So from this plus sign, there's a plus sign. If you click this plus sign, you can install this module. And if you click this model, then you can see there is something known as the general linear model. So click on this general linear model. And here again, the interface is very much same, except that you will get effect size here. Can you see like beta, partial eta square, and all these effect sizes here? So those of you who wish to perform this, otherwise that is also okay. So this LOS you move to dependent variable, age as a covariate, and let's say gender you have moved as a factor, pre-op LOS as a covariate. I'm only taking 3 right now. So it again gives you, here it gives you a important summary model information. The interface is little different. So it gives you like linear model fit by OLS, that is we have read ordinary. Yeah, that's what I said, that you have to, with this plus side, sorry, you have to install this module, this linear model. This doesn't come as a basic one. You have to install this linear model. So then it like you can enter, this shows the R square, adjusted R square. And this is the ANOVA, the overall sum of square degree of freedom. You can leave that and it gives you the partial eta square also. The rest of it is same. Only for effect size you can use that. I'm not going into, there are many other effects. If you see the assumption checks, you have got a little different normality, homogeneity, it is there, QQ plot, it is there, but all those autocorrelation and variance inflation factor, that is not here. So probably good one is that only, but for effect size, you can use that. Options, again, those options of saving predicted and residual, it is here also. So have you understood up till this point? What is the difference in linear and in GLM? No, the same I said that if you wish to give effect size, that is okay. Otherwise, use the previous one. Don't use this. Use this regression only. I mean, that's a little advanced. That's why maybe if you don't wish to, I think for you people, the regression is okay. Don't go by GLM. Yes. So now you practice the interaction, the same example, age and gender. As a confounder and as an interaction, plot the curve, interpret it, and see the change in beta. Or you can do it with any other variable also and see the change in beta and see the interactions, whether it is significant or not. And plot the graph. So Anand, can you please share that distance which we are talking? Let me pronounce it. It is Mahalanobis distance. Mahalanobis distance. Is it visible to all of you, my screen? Let me see the chat. Okay. Thank you, Fazana. So this is again, this Mahalanobis distance is for the high leverage that I think in the beginning I have discussed about this, that this is again a high leverage point. So Cook's distance takes this into account. But if you wish to see this, you can click this also. And you can go and see that in the data. This I have downloaded that 2.6.26 version. If you go to the data, you can see the distance. So this was the same. And again, there was one question by, I think, one participant regarding the sample size. So if you open this GPAR, and here from the statistical test, from this window, you need to select the, if you just use this drop down menu, you can see linear multiple regression, single regression coefficient. So I will click this, and then you have to use that determine. So when you click this determine, here there are two options. Either you need to do it by this variances, or you need to use this direct. So in direct, you can use this partial R square or R square. So R square was 18% in our case. So I have entered that. And when you will click that, you will close this. This will appear here, this effect size or F square, 0.219. And then you need to put like number of predictors. So number of predictor, let's say I have 4. So I'll click on 4, and this is the alpha and beta error, which we generally alpha error we keep at 5% and beta error at like bar is 95. You can reduce the power also. If you wish to keep the power as 80%, you can keep it as 80 and then press calculate. So the total sample size is 30. If you increase the power, by default, it takes like 95. So then if the number of predictor is 4, and then if you press calculate, the total sample size is 51. So that is how you can calculate the sample size in case of, and this GPAR is very nice. You will have all the options here. So for advanced calculation of sample size, For modeling and prediction, you can use the GPAR for the sample size calculation.
And
So-
G-Power is a free software.
Yeah, it is free. It is free. You need to download it as like we downloaded the Jamovi, so you need to download that, and then you can use that. Close canvas.
Then from Jamovi, we can download G-Power.
No. The way have downloaded the Jamovi,
Okay.
go to the web and just click that download GPAR, you can download it.
Ma'am, I have one doubt.
Yeah.
Ma'am, for confounder, you told that using linear regression, it will automatically adjust for confounder. Suppose we got significant interaction, then how to report it?
You can only report that yes, these two variables are interacting, so there is a interaction between these two variables.
So, ma'am, that is a positive thing only. No? That's why it is getting changed or something. The ultimate outcome.
You are talking of interaction.
Yes, ma'am, interaction.
Yeah. You cannot say positive or negative. That's the underlying phenomena behind. So because of that interaction, the mean which you are seeing, that is not the effect of that variable, but another variable is also playing a role.
Okay.
I think so. So someone said, I think, ma'am, can you repeat the interpretation of interaction? So interpretation of interaction is like, let's say, if I
Ma'am, we used heart disease and age, and I think we found it significant. Could you just do with that, ma'am?
Okay,
Heart
sure.
disease and
So I'll go to this regression. So in regression, you are saying dependent variable as LOS. And here, age.
disease.
But in our case, it is not p-value is 0.8. This. Did you take any other variable also? Like any other predictor? Yes, because 0.8 p-value is very high. Did you see this estimate as significant? You have to see this column. If P is not significant, you don't need to see all these factors. If P is significant, if interaction term is significant, then only.
Okay, ma'am. I think we did something wrong.
Okay, you can again check it if it is there.
I think we found that heart disease was a confounder.
Yes, it can be. That you can check. See, all these we have just told you statistically, you can keep on. And if there are multiple, again, the best is you should have some theoretical background regarding a variable, but you can do it in the statistically also.
So can you just do that along with confounders and show, ma'am? Because then it contradicts our way of saying.
Okay, so
Or
which
is it, yeah.
you are asking me to do what? Can you please repeat?
What?
Heart disease as a confounder.
Yes.
Okay.
Heart disease as a confounder, yeah.
Okay, so I am in previous complications I have put here. Oh, okay, so we are doing it with 4 variables. But I need to, let me see. This one, then it will come in block 3, the gender, and then block 4, if I move heart disease. So what is your primary variable? Primary variable means primary predictor on which you want to see the effect of heart disease. Because this is the model for, I took heart disease. So let's say for that you need to see like which one is the primary. Suppose I'm seeing this model 1. Age, if I see between model 3 and model 4. So model 3, if I'm seeing effect on, let's say gender, it is 0.34 estimate. And if I have this heart disease also, this is the same 3.34. Again, if you see, but the better is like, let me see. So you want the primary predictor is what?
Ma'am, you remove that pre-op. We don't want that pre-op.
Okay. So age and heart disease?
Yes, age and heart disease.
Okay. So let me move. Just a sec. Age and heart disease I will put here. So here in model 1, the age is 0.01. And in model 2, it is same, 0.01. No change in estimate. See, age is 0.01 in model 2. And in model 1 also, age is 0.01. But that will not affect. So it is not here to age, the same coefficient is remaining the same.
But then what about the p-value there?
P-value, you don't see, you have to see the p-value. Here you have to see the coefficient. In interaction, you have to see the p-value. In confounder, you have to see the coefficient.
Okay.
Did you get it? Probably you were seeing the opposite way. You were seeing the coefficient in interaction and p-value in confounder. That's why probably that 0.03 was significant, which was the coefficient. But for interaction, you have to see the p-value. For confounder, you have to see the coefficient.
Okay.
Ma'am, if the p-value in the interaction comes significant, then how we will interpret the coefficient?
That in that case, you don't interpret. In that case, it's better to give the estimated marginal mean, which I have just said. You can include that interaction term, and let's say if it is significant, you can say that its level is different at each level. That means the estimated marginal mean will be different. It will be adjusted for that particular variable, and then you can give the estimated marginal mean.
Okay,
In
ma'am.
that case, coefficient interpretation will be let me try one. So you are saying that if age, let me try it out. Let's say age and gender, although it is not significant, but if it is significant, so right now I will another variable. Okay, another variable I want to have as a, let's say age and gender. So it is not significant, but the coefficient is minus 0.01. So that means the reference level is male, the reference is female here. So you can say that with age, in the higher age group or with increasing age, the difference in male and female length of stay will be 0.01. That's how we will interpret. If you want to see it in the form of coefficient, otherwise, generally, what we do, you give the estimated marginal mean. So in here, what I'll do, this age and gender, I'll move here, and then it will give you the estimated marginal mean. that you can report. Otherwise, you just say that there is an interaction. Is it okay? So Suresh is saying,
Will it be different if we just put them in a different way, like put the
yeah, that's what I think
gender?
Suresh has also writing.
Yeah.
Age, please put heart disease first. Okay.
नहीं कोई फर्क नहीं पड़ेगा करके दिखा
Let me do it.
ऊपर नीचे कर दीजिए वहीं पर नहीं उसी से नहीं ऊपर नीचे हो
नहीं, gender heart disease है नहीं इसमें.
Ma'am, I was in the same room and simultaneously I did the same process again. But I think we were confused about like what we have taken as a primary predictor.
Okay, so like he's saying, Dr. Suresh is saying take heart disease as a primary predictor.
Primary. So we took a primary as a heart disease and again we
Yeah,
were
let's try that. Let's try that once.
ऊपर करेगा ऊपर
Okay.
लॉक होता है उसको कोई फर्क नहीं पड़ेगा नंबर पेशेंट ये चाहिए 0.86 से 0.74 हो जाएगा डालते ही रेक्टर के सीक्वेंसिंग में थोड़े फर्क पड़ेगा सेम है 0.74
See, initially in model 1, it is 0.86. And in model 2,
Yes.
0.74. Yes. So you can say that it is a confounder, yes, because the coefficient is changing. So age is a confounder. Because now the coefficient is in the initial one, it is 0.86, but after this, it decreased by 12. Excuse me. So you are right.
Does it happen, ma'am, like that? What is?
Yeah, because predictor is different now. Predictor is different. Your primary predictor you have taken as a heart disease. So it happens, yes, you need to define like on what you are seeing the effect of it. So primary predictor you need to decide. And then you can see the effect of it. And that should not be only on the basis of statistics. There should be some primary like literature evidence and all those things is also important. It is not only the statistics part because statistics part comes only from that knowledge.
Okay, now the confounder is positive. I mean, it is significant. But then if you look at the interaction, I think it is not significant.
Interaction
that's-
is different.
Okay, yeah. So that is okay. So
Yeah.
we'll come only on the confounders.
Yeah, interaction is different.
Yeah, okay.
Okay, so if that means if this is okay up till this point, then you may practice for 1 week, and then again on Friday we are meeting again with the logistic regression because now you have done with the linear regression, seen simple and multiple, and in the next week we'll discuss the logistic and the proportional. Binary logistic, proportional logistic, and the multinomial logistic. The other three types of logistic, three types of logistic regression, ordinal and multinomial. So I think there's no end of the day exercise. So we will meet again on Friday. Next Friday. Next means coming Friday.
Ma'am, just I have one question regarding my PhD.
Yeah, Farzana.
Ma'am, actually, in my study, one objective is to assess the early childhood development, and I have used total 4 tools in that assessment.
Okay.
Now I have a data in my hand, and now I am not very much clear how should I do analysis. Like for every tool, there is a different manuals for calculating the score and categorizing the whether there are delay or not. So is there any standard method where I can compile all the tool score and calculate?
But all the tool means what will be the basis of like compiling all those tools? Because there should be some basis of having an aggregate score. 4
Yeah.
tool means like you are saying like all those anthropometric tool.
No, early childhood development tool.
Okay, so which tool? Can you name some tool?
Yes, ma'am. So,
Like
for
there's a Trivandrum scale.
first is Ox NDA, second is Inter NDA, third is IDLA, and four is CREDI.
I have no idea, dear. It's
So,
specific. So probably you can WhatsApp us separately. We'll see. We'll try it first because I also need to understand. I have
okay.
not. So probably let me see that also, all that scale. You can WhatsApp or you can mail. Let us first see that, and then probably by next Friday or so, we will be able to convey something to you.
Sure, ma'am. So I'll name all the tool. I'll share data if you
Yeah,
want.
something we need to see before we actually conclude because yours is very specific.
Yes, ma'am. Because basically I calculated Z score for every tool. So that for that मैं वहां तक पहुंची, but उसके आगे how should I standardize that Z score for all the tool where I was stuck. So
You can send it once. We will try to see it in the coming week.
okay, sure, ma'am. And the second thing is Dr. Anis Sinha. I think you know him.
Oh, yes, I know him very well.
He is my supervisor, and we have a communication about you.
Oh, that's good. Yes, he is very close. Like I know him closely.
Yes, sir. So he
Well, good,
conveyed
good.
regards to you.
Congratulations. Thank you. Convey the same to him as well.
Thank you. Okay, thank you, ma'am. I'll send.
Okay. Bye-bye.